All right, in this lesson we're going to be looking at infinite geometric series. And an infinite geometric series is just a geometric series with an infinite number of terms. And the thing we need to remember about this is that the sum may or may not be finite here, okay? We kind of are under the assumption that if we have an infinite number of terms, an infinite number of numbers being added together, that it's going to equal infinity. And that's really not the case. We will end up with things where we have an infinite number of terms being added together, but when we add them together, it equals a finite number like 5 or 2 or 3. All right, so this may or may not be finite, and there's specific situations where it may or may not be finite. Okay, for example, if I look at the first one, it's telling me to plug in a 1, and then a 2, and then a 3, and then a 4, and then a 5, and then keep going forever. Okay, so I'm going to go from 1 to infinity here. And what we'll do is we'll just plug in the first couple to see what this thing looks like. So if I plug the 1 in, it gives me a 6. If I plug the 2 in, it gives me a 12, a 3 in, a 4 in, and I could keep going, a 5 in, and I'll stop there. And that keeps going forever. So the first thing we do is we look at each term, and it says down here, what do you notice about the value of the series, the values of the series, okay? So the values of the terms here. As we look at these terms, the terms are getting bigger and bigger. I'm doubling them each time. I'm multiplying by 2 each time. So the terms are getting bigger and bigger and bigger and bigger and bigger. So if I were to continue this forever, my last term would appear to be infinity here, okay? Because this thing gets bigger and bigger and bigger, the last term is going to get closer and closer to the value of infinity because it keeps getting bigger and bigger. So the thing we need to notice here is that the values get closer to infinity. I should write closer to infinity. Okay? So the values just keep getting bigger. So then what does that tell us about the sum? Well, if we were to actually look at the sum, like if I did s sub 1, that's the sum of the first term, that's a 6. All right? If I did s sub 2, that would be the sum of the first 2 terms, that would be an 18. If I did s sub 3, the sum of the first 3 terms, that would be a 42. If I did the sum of the first 4 terms, it would be a 90. If I did the sum of the first 5 terms, it would be a 186. And of course, I could keep going, and this thing keeps getting bigger and bigger and bigger. It looks like when I look at the sum keeps getting larger. So if each term is if the terms are heading towards infinity, and as I add them together, it keeps getting bigger and bigger and bigger, it means that the sum is also heading to infinity. So this is also getting closer to infinity, all right? This is the situation we would expect, okay? If I have an infinite number of numbers, they're going to keep getting bigger, and when I add them all together, it's going to equal infinity, all right? This is like the typical situation. This is what we'd expect to happen. However, if we look at the next one, I'm going to ask the same couple questions. We're going to do the same kind of thing. If I were to start plugging this one into my calculator, and we'll just do this one as decimals, okay? I'm just going to find the first couple terms again. So if I find the first term, if I plug a 1 in, that gives me a 4.8. If I plug a 2 in, it looks like it gives me a equals plus, it looks like it gives me a 0.96. If I plug a 3 in, it gives me a 0.192. If I plug a 4 in, it gives me a 0.0384. And I'll do one more here. The next term would be a 0.00768. All right? So we can kind of see something happening here. It's not quite what happened before. So what do we notice about the values of the series? Well, if I look at the value of each term as this thing continues, as I start to plug in more and more terms, now the terms are getting smaller and smaller and smaller, and the pattern is as I'm dividing by 5 each time, so they're getting smaller and smaller and smaller. So instead of heading to infinity, this one's actually heading to 0. And one of the other answers I always get is that it's heading to negative infinity. But keep in mind, negative infinity, the numbers would be getting larger, but it would be getting larger in the negative direction. And this is not the case here. The decimals are getting smaller and smaller and smaller. They're approaching 0 this time. So the values on this one are getting closer to 0. And so the second question here, what does that tell us about the sum? Well, think about it. Before, the last term was going to get closer to infinity. So the last term will say, if I can make it that far, the last term would be infinity, so the whole thing went to infinity. Well, this one, the last term, this is getting closer and closer to it. If I made it all the way out to infinity, the last term would be 0. And if eventually I'm adding nothing to the sum, will the sum keep increasing to infinity? And the obvious answer there is no, all right? If I start adding nothing, the sum is going to stay where it is at some point, which means I'm going to get a finite solution. I'm going to get a number that's not going to infinity, that's not continually increasing, all right? So now the question is, where is this thing headed? Well, let's do the same thing we did before. S sub 1 would be 4.8. That's the easy one, okay? And then S sub 2, we just have to add the first two terms. So S sub 2 equals a 5.76. Oh, that's a little close. Let me space it out a little bit more. S sub 3, I've got to add the 0.192. That gives me a 5.952. S sub 4, I add the first four terms together. That gives me a 5.9904. S sub 5, oh boy, I'm making a lot of stray marks here. Let me get rid of those. S sub 5, I add the first five terms together, and this is all the terms that I have, so I'll stop after this one. But hopefully we kind of see what's happening here. I got 5.99808. And so when we look at this thing, where is it heading? Oh, look at the numbers. It looks like it's getting closer and closer to a value of 6. So it looks like the sum is getting closer and closer to 6. And that is what's happening here. When you look at this one, yeah, I'm getting closer and closer to 6. And if I made it all the way out to infinity, it would equal exactly 6. Okay? And so what we have here, the big difference between these, one of them is going to infinity, one of them was going to a finite value. The difference is in the R value. When we look at the first example that we did right here, the R value is a 2. When we look at the next example, the R value is a 1/5. And so that fraction is the real key to this thing. This will go to a finite number if I have a proper fraction for my R value. Anything else, it's going to diverge to infinity. Okay? And so when we look at this thing, we really have to have an R value that's a proper fraction that's between -1 and +1, and then we'll be able to find a sum. Okay? And so what we have a formula for this sum, and it looks like this. Okay? So the formula is S equals A sub 1 over 1 minus R. But again, this only works and can only be used if the R value is between -1 and +1. Okay? And this formula should look familiar. This actually comes from our geometric series formula, which was this one. S sub n equals A sub 1 times 1 minus R raised to the n all over 1 minus R. And what happens here, if we think about this R value, I take this up here and think about the R value. Since the R value is a fraction, think about what happens to fractions. Let's say R was a 1/2. When you raise 1/2 to the first power, you get a 1/2. When you raise to the second power, you get a 1/4, a 1/8, a 1/16, a 1/32. So you can see what's happening to the fractions. The fractions getting smaller and smaller and smaller and smaller and smaller. And so what happens here is when I have a fraction for the R value, if n goes to infinity, if I raise it to the infinite power, this whole thing right here gets canceled out and becomes a 0. And if that whole thing becomes a 0, 1 minus 0 is a 1, times the A sub 1 just leaves me with the A sub 1 in my numerator. That's where this formula comes from. Okay? Because that R value is a fraction, as n goes to infinity, that whole thing goes to 0, which means I can get rid of that whole thing, so it gives me a much simpler formula. Okay? So keep that kind of stuff in mind. All right? It gives us a much simpler formula because that whole second piece goes away. All right? A sub 1 is still the first term. R is still the common ratio. It's the thing we're multiplying by. But again, we'll only use this between -1 and +1. Okay? And the word that I'll use a lot of times when I refer to the R value is I'll talk about this thing converging or diverging. Okay? Converging means it's zeroing in on a specific value, a finite value. Diverging means it's shooting off to infinity. All right? So when we look at each of these, it says find the sum of the infinite geometric series if it exists. And that's really important. If it exists. This will only exist if the R value is right, if the R value is between -1 and +1. So if I look at the first one, I just need to identify the R value for this one. The R value this time looks like it's going to be a 3/4. Okay, I'm multiplying by 3/4 each time. And the question is, does that fall in my acceptable range? And the answer is yes, that's between the -1 and the +1. So that means I can find the sum. This is going to converge on a specific value. So S equals A sub 1, which is the 1/2, over 1 minus R, which is the 3/4. So I plug each of those things into my formula. Now I just need to simplify. When I simplify this guy, it gives me a 1/2 over 1 minus 3/4 is a 1/4. And now dividing by a fraction, the same as multiplying by the reciprocal, that gives me a 2. So when I take the infinite number of numbers that I have here and add them all together, it equals 2. Okay, that's what's tough thinking about these for some students. How can I have an infinite number of things added together and it equals 2? Well, it just does because those values get smaller and smaller as we go. All right. If I look at the next one, we have to identify the R value. The R value for this one looks like a 3/2. Okay, so it's 3 over 2. And when I look at that R value and I ask, does it fall in my acceptable range? The answer is no. Okay, it's got to be a proper fraction. This is an improper fraction. It's got to be between -1 and 1. This is not between -1 and 1. It's outside of that realm, which means I can't even find the sum of this one. This one's going to diverge, which means it's going to go to infinity. So what I say here is I say the sum does not exist. So I'll write D and E for does not exist. That's one example. Answer I will accept. I'll also accept if you simply say that it diverges. Okay, what am I doing? I'm putting a parenthesis down like a crazy person. So I'll also accept if you say it diverges. I'll also accept that as an answer. So either it does not exist or it diverges, which means it's not going to a finite value. It's shooting to infinity. Okay. The next one, the R value this time, it's bouncing back and forth between positive and negative, which means my R value is negative, and it looks like I'm multiplying by 2 if I ignore the sign, so I'm multiplying by a -2 each time. So I look at that, and it doesn't fall in my acceptable range. Once again, it's not between -1 and +1, which means this one does not exist either. Okay, so it does not exist, or you say it diverges. And if you want to abbreviate that, that would be fine also. Okay, so I'll accept either one of those as an answer to this. All right. The next one, again, the R value, got to identify the R value first. The R value here is a 1/2. Well, if the R value is 1/2, that means this thing is going to converge on a specific value because 1/2 is between the -1 and the +1. So now I can plug it into my formula. S equals A sub 1, which is the 20. That's the first term, over 1 minus R, which is the 1/2. So that's 20 over 1 minus 1/2 is a 1/2. And now dividing by a fraction is the same as multiplying by the reciprocal, which is a 2 over 1, which gives me a 40. Okay, so I have an infinite number of numbers added together and it equals 40. All right. The next one, this should look familiar. This is the example from the previous page. But if I'm going from 1 to infinity, really I just identified two things. The R value. The R value for this one is 1/5. Okay, so that's in my acceptable range, so I'm going to keep going. I need A sub 1, so I actually have to plug a 1 in here for n. And when I do that for this one, it gives me the 4.8, which as a fraction is going to be 24/5. And so now I plug it in to find the sum. So the sum equals A sub 1, which is the 24/5, over 1 minus R, which is the 1/5. And then from here, let me pull my pen back up. I'm trying to write with an eraser. So that's 20. Oh, I missed a step. Let me show all the steps because I know we're not great at working with fractions, some of us. Over 1 minus 1/5 is a 4/5. And now again, dividing by a fraction is the same as multiplying by the reciprocal. So this is a 24/5 times a 5 over 4. And now I can reduce, I can cross reduce. The 5's cancel out to a 1 and a 1. The 24 and the 4 cancel out to a 6 and a 1. I multiply straight across and it gives me a 6. Okay, which is not a surprise. That's what we said it was going to be. That's what we saw it heading towards earlier. Okay. If I look at the next one, I do the same thing. The R value this time is a -3/4, which falls in my acceptable range. It's between -1 and +1. So A sub 1, I plug a 1 in. So A sub 1 equals a 16 when I plug that in, and I just plug it into my formula. So the sum equals 16 over 1 minus a -3/4. And keep in mind that is minus a -3/4, which is like adding the opposite. You might have to get common denominators here, and that's okay. That's going to be a 7/4. And now dividing by a fraction is the same as multiplying by the reciprocal. So that's going to give me a 64/7, which I guess I would say accept that as an answer. Or you can write it as a 9 1/7. Okay, so leave it as a fraction or a mixed number, not as a decimal. All right. So again, when you're looking at these things, check the R value to see if it's between -1 and +1. If it is, it converges. You can use your formula. If it's not, it diverges. So the sum does not exist.